Hello, Assalamualaikum. My name is Muhammad Nashauki Berosli. So this is a Group 26 design of automated Belacan shrimp paste factory. So we continue with study agenda, which is a project introduction, system architecture, governing equations, engineering drawing, proof of concept and optimization, project management, finance and conclusion. So the project background is Belacan, also known as shrimp paste. This is an essential ingredient in Southeast Asian cooking. It is made from fermented dry shrimp, which gives it a distinct umami flavor. Belacan is widely used in traditional recipes from countries like Malaysia, Indonesia, Thailand and Philippines. Malaysians on average consume up to 1.41 grams of belacan per day. The current production of belacan often involves relatively primitive techniques that require significant manpower and time. The grinded shrimp paste need to be sun-dried for at least 4 hours under optimal conditions and can take up to 8 hours in less than optimal conditions. Despite the labor-intensive process, belacan remains a culinary treasure cherished for its unique taste and cultural significance. Efforts are being made to modernize the production process without compromising its traditional flavor and the characteristic. So we continue with problem statement. For the first problem statement is high process time. Current drying process can take 8 to 16 hours due to weather dependency. And then inconsistent and unpredictable drying times affect production efficiency. Delay in drying impact the overall production schedule and delivery timelines. For the next problem statement is high labor cost. For the high labor cost, manual drying and packaging are labor intensive tasks. High reliance on manual labor increase production costs. Risks associated with worker fatigue and inconsistency in product quality. So next I will present about objective and scope of project. For the objective, to design an automated shrimp paste belacan factory where production time could be shortened without compromising product quality, to produce conceptual design based on selected data, to produce detailed design and equipment detailed drawing, to assess the expense and sustainability of the project. So for the scope of project, the project scope include designing the machinery and supplying assembly and detailed drawing, develop set of systems that require automated the file process, conduct detailed calculation and analyze on equipment, provide engineering drawing in compliance with engineering standard.
Next is the system architecture of this project. This serves as a guide for us to identify the crucial components in this factory. From this system architecture, we have planned out the key tasks that we have to accomplish to make this project a success.
So next, I will be presenting the governing equation used for this project. So the first governing equation is for grinder. So the first equation is motor speed. This equation relates the motor speed in revolution per minute to two crucial variables: the angular velocity of the motor and the diameter of the grinding wheel. The angular velocity represents how fast the motor shaft rotates, while the grinding wheel's diameter detects the distance traveled by the wheel per revolution. So for our project, assuming a motor speed of 10 rpm and a grinding wheel diameter of 1.3, we can calculate the rotational speed of the grinding wheel as follows. The motor speed that we get is approximately 146.91 rpm. So for the next equation, grinding capacity, this equation relates the grinding capacity to two essential variables: the mass flow rate of meat and the time taken. The mass flow rate represents the amount of meat processed per unit time, while the time is the duration over which the meat is brought. And lastly, for this machine, the blade speed equation. This equation relates the blade speed to two key variables: the blade diameter and the motor speed. The blade diameter represents the size of the grinding blade, while the motor speed is measured in revolution per minute. By using this equation, we can determine how fast the edge of the grinder's blade moves during operation. So for our project, the blade diameter is 0.3 meter and the motor speed is 2000 rpm. After applying the values, we get 31.42 meter per second of blade speed. So next, moving on to the next common equations, dryer. So for the first equation, velocity of conveyor in dryer. Using the formula for velocity, which is distance divided by time, we obtain the following results. The required speed for the conveyor is approximately 0.00125 meters per second according to the calculations. Next, the second equation is volume of krill on conveyor belt. So the first step was to convert the thickness of the krill layer from millimeters to meters, which gave us a thickness of 0.07 meters. Next, we calculated the volume of the krill layer on the conveyor. So to do this, we multiplied the area of the krill patch, which is 6 square meters, by the thickness we just converted to meters. So for the weight of krill based on average density, we determine the weight of the krill layer by multiplying the volume we calculated with the average density of krill, which is approximately 1040 kilograms per cubic meter. Next, governing equations for conveyor. To calculate the weight of conveyor, we can use the formula volume times density. So based on this formula, we get the weight of the conveyor to be 168 kg. Next, the belt sack. The formula is 1% of the belt span. The assumed belt span that we use is 4 meter, so 1% from 4 meter is 0.04 meter. Now for the effective belt span, it is the distance between two adjacent rollers. The formula is conveyor length minus belt sack. So after applying the values we get before, the effective belt span is 3.96 meter. Now moving on to the number of rollers. The formula is effective belt span divided by roller spacing. After inserting the values, the number of rollers we get is 6 after rounded down. Next, the roller diameter. So for roller diameter, we need to choose a roller diameter that is 3 to 5 times the belt thickness. So the formula that we use is 3 to 5 times the belt thickness. So after calculations, the value that we get is 18 millimeter to 30 millimeter. And the last equation is to calculate the torque required for the conveyor. The formula relates the torque required for the conveyor to three crucial variables: the total weight on the conveyor, the belt weight, and the radius of the roller. Additionally, we have the coefficient of friction, which accounts for the resistance between the belt and the roller. So after plugging in all the values, the required torque for our conveyor system is approximately 4.6556 Newton meter. Now for the last communication is for the shaping and fashioning. So firstly, the screw pitch equation. The formula relates the screw pitch to the screw diameter. So the screw pitch determines the distance between consecutive threads of the screw, which in turn influences the conveying information of the Belacan as it moves along the conveyor. So based on the formula, the calculated screw pitch that we get is 1312.5 millimeter. Next, the motor speed for the machine. The equation used is the same as mentioned beforehand on the part on the grinder governing equation. So after plugging in the values, the RPM of the motor speed is 136.91 RPM.
For this part, I will present the engineering drawings that we have come up with for this project. I will be highlighting the key features that we have designed for each of the subsystems of this project. For the first machine is the grinder. We have designed it so that it is able to produce the correct consistency of belacan that we want and is able to produce the required process time to achieve our target production rate. The design process of this grinder is shown previously in the governing equation. Next, for our dryer machine, we have gone with a convection-based dryer.
From literature review, we have come up with the optimal design encompassing the temperature and airflow speed to ensure the quality of the belacan is preserved and the belacan is adequately dried during the process. Moving on, the conveyor plays a crucial role in this project as it is responsible to move the materials from one system to the other. For this, we have designed it so that it is able to deliver the material at the correct time at rest so the factory can run smoothly. We also ensure that the design for this conveyor is able to withstand the load that will be put on it. Next, the shaping and portioning machine. We have adapted design from an extruder machine to be used for shaping and portioning the belacan. This machine works based on a preset time for it to cut the belacan into desired sizes. We also designed so that it can fit belacan at our desired rate. For this machine, we have decided to take an off-the-shelf product. We modeled it based on the exterior shell and dimensions so that the packaging machine can proceed with the sizing and the layout of the factory.
Next, we move on to the proof of concept and technical specifications of the project. So on the left, we can see a 3D view of the plant layout. The total dimensions for this plant is 13 meters by 7 meters, and this plant is fully connected via conveyors. On the right hand side, we can see the key technical specifications for this plant. Next, we move on to the finite element analysis of the conveyor component for this plant. So the results of the conveyor FEA analysis is as shown in this description on the right. So the material chosen for the conveyor is 316 steel, which has a tensile strength of 515 to 827 megapascals. And from the simulation on the load conditions that we have set for 400 kilograms of krill, we find that the maximum stress experienced by the conveyor is 0.696 megapascals, which is far lower than the tensile strength of the material chosen. And the maximum deformation experience is 0.00549 millimeters, which is a negligible amount of deformation. The next proof of concept that we did was FlexSim simulation. This is to test out the throughput of the factory and if it is able to produce our objective goal of 5,000 kilograms of belacan per day. The first objective is achieved as this factory is capable to produce 6,000 kilograms of belacan per day at full capacity. And from this simulation, we also found that one grinder is not sufficient to produce 5,000 grams of belacan per day as it did not meet the minimum requirement for production rate. So our solution to this is to put in 3 grinders. So from this we can see in the simulation that 2 grinders are running at 50% capacity while the third grinder is at ideal most of the time. This is good as we will have a failsafe for if when the grinder is broken down. The other 3 processes, which are the drying machine, the shaping machine, and the packaging machine, are running at almost full capacity most of the time.
Moving on to project management part. For the installation and building of this factory, we have created a 3-level work breakdown structure, WBS, to visualize the process required to put up this factory. It starts with site preparation that consists of clearing and leveling the site, building interior setup, which is partitioning, electrical wiring and lighting, and also setting up safety measures and signage. Then it continues with building construction that consists of construction of the main factory building, installation of walls, roof, and flooring, and building interior setup, which consists of partitioning, electrical wiring, and also lighting. Once the building is at least 80% ready, we can continue with the procurement of the equipment and machinery. It consists of research and selection of semi-automated belacan production equipment, procurement and delivery of machinery, and installation of equipment and machinery. Lastly, before the factory is ready to operate, we started with training and hiring. It consists of hiring of additional staff as required, training of existing and new staff on operating machinery and automation system, and lastly, safety training and compliances.
Here are the breakdown of the finances for this project. The first is the capital cost. For the capital cost, we take into the consideration of the processes, which are the grinding machine, drying machine, shaping and portioning, packaging, and also the building of the facility to place all of the machines. This all comes up to a total of 199,449 ringgit and 28 cents. And we also took into consideration the labor costs for construction workers, project managers, and electricians during the building stage and also the installation stage of all of the machines and also building. And the third cost that we took into consideration was the daily operational cost, which the things that we took into consideration were raw materials, electricity, water, factory workers, and also maintenance. Then we calculated the revenue that we could produce with 5,000 kilograms per day, and we chose to sell our product at 10 ringgit per kilogram, which is below market retail price as we are acting as wholesalers. And from these calculations, we also considered 24% profit tax from the government. And from there, we found that the return of investment period for this project is 112 days.
To summarize the project, the conclusion is ability to improve quality and productivity of processing belacan, delivery and an innovative and creative solution to increase belacan production, using CATIA to know the machine tensile strength and maximum stress and deformation, using FlexSim to estimate the production of belacan based on the production plan. That's all from us. Thank you.